Have you ever just stopped and wondered, what is everything really made of? I mean, when you get down to it, what's the most fundamental stuff in the universe? It's a huge question, right? And the answer, it turns out, takes us all the way back to the very first moments of creation. So let's dive in. Today, we're going on a pretty wild journey. We're going to a time before atoms, even before the protons and neutrons you learned about in school. We're headed straight into a state of matter so extreme, it's basically a primordial soup. Yep, we're talking about melting the very building blocks of our reality. So here's the game plan. We'll peek inside the proton, then we'll get to know this primordial soup. After that, we'll see how scientists are literally recreating the Big Bang in a lab, explore the absolutely bizarre properties of this ancient matter, and finally, we'll see why this is all a window into our own origins. All right, first things first, let's go inside the proton. You kind of have to understand what's normal before you can really appreciate just how incredibly weird things are about to get. You know the basics, right? Everything you see around you, the chair you're on, the air you're breathing, all of it is made of atoms. And at the very heart of every single one of those atoms is a nucleus, which is made of protons and neutrons. These are the classic, familiar building blocks of our world. But here's where the rabbit hole gets deeper. Those protons and neutrons, they aren't the bottom floor. They're actually made of something even smaller, even more fundamental. And that brings us to these guys, quarks and gluons. A proton, for example, is made of 3 quarks, and they're held together by gluons. The name is a total giveaway. Gluons are the particles that carry the strong nuclear force, which is the most powerful force in the universe. They literally glue the quarks together so tightly that you can't ever pull them apart. Well, not under normal conditions anyway. So what does happen when normal goes right out the window? What happens when those unbreakable bonds that hold matter together actually break? You get this. Quark-Gluon Plasma, or QGP. It's a state of matter so incredibly hot and dense that protons and neutrons literally melt away. The quarks and gluons bust out of their confinement and just roam free in this incredibly hot, dense soup. And get this. This isn't just some wild theory. This is what the entire universe was made of for the first few millionths of a second after the Big Bang. This comparison here really nails the difference. On the left, with normal matter, you can think of quarks as being stuck in these tiny, inescapable prisons, the protons and neutrons. But on the right, in the Quark-Gluon Plasma, the prison walls have completely dissolved, the quarks and gluons are free, deconfined, just swimming around. It's a total change of state, kind of like ice melting into water, but on a scale that is just, well, cosmic. Okay, so this stuff existed for a microsecond almost 14 billion years ago. How on earth could we possibly study it? Well, believe it or not, scientists are doing exactly that. They're recreating the conditions of the infant universe right here on Earth. To even begin to make Quark-Gluon Plasma, you need temperatures that are just astronomical. We are talking about 10 trillion Kelvin. That is hundreds of thousands of times hotter than the core of our own sun. It is, without a doubt, one of the hottest things humanity has ever created. And where does this all happen? At some of the most massive and complex scientific instruments ever constructed. We're talking about places like the ALICE experiment at CERN's Large Hadron Collider over in Europe, and the STAR and Phoenix experiments at Brookhaven National Lab's Relativistic Heavy Ion Collider in the US. So, how in the world do they pull this off? It's basically a 4-step recipe for cosmic creation. First, you take heavy atoms like gold or lead, and you accelerate them to 99.999% of the speed of light. Then you smash them into each other head-on. The impact is so unbelievably energetic that for just a fleeting, tiny fraction of a second, you create a microscopic fireball that's hot and dense enough to become quark-gluon plasma. And just as quickly, it cools and vanishes, exploding into thousands of new particles that massive detectors track to figure out what just happened. Okay, so we can make it. But what is this stuff actually like? Well, when scientists finally created QGP, what they found was completely surprising. It wasn't at all what they were expecting. Here's the kicker. Everyone thought this soup of quarks and gluons would act like a gas, right? With particles just whizzing around chaotically. But nope. Instead, it behaves like a nearly perfect liquid. It has almost zero viscosity, which means it flows with practically no friction at all. It's a more perfect fluid than anything else we know of in the universe. It's truly the universe's most perfect liquid. So how do scientists know for sure they've actually made QGP? They look for clues in the wreckage of the collision. They see something called collective flow, where all the particles move together in a coordinated wave. That's a dead giveaway you're dealing with a liquid, not a gas. They also see jet quenching, where super high-energy particles get bogged down and lose steam trying to push through the dense plasma.
This is all really cool physics for sure, but what's the big picture? Why does this really matter? Why spend all this time and money to create a microscopic drop of the universe's first stuff for less than a split second?
This is why. This is the whole ballgame. By creating and studying Quark-Gluon Plasma, we are literally looking back in time. We're getting a direct peek at what our universe was like just 1 microsecond after the Big Bang. It's the missing link between the Big Bang itself and the moment the universe cooled down just enough for this plasma to freeze out and form the very first protons and neutrons, the stuff that would eventually become you, me, and everything we see. And the impact goes way beyond just understanding the Big Bang. I mean, to even build these experiments, you have to push technology to its absolute breaking point. We're talking about inventing more powerful magnets, more advanced cooling systems, and then there's the data. You have to process petabytes of it, which drives massive leaps in computing. And those breakthroughs, they don't just stay in the physics lab. They spin off and help improve things like AI and supercomputer models for all sorts of fields. So, in the end, the best way to think about quark-gluon plasma isn't just as some weird, exotic state of matter. It's better to think of it as a fossil. It's a perfectly preserved sample of the universe at the moment of its birth. And we figured out how to bring that fossil back to life for an instant, just so we can study where we came from. I mean, think about it. We've managed to recreate the universe's primordial soup, its very first, most perfect liquid. It just makes you wonder, what other secrets about the cosmos are out there, just waiting for us to figure out how to unlock them next?